All right, so today we're going to continue our discussion of renormalization with renormalization of local operators and critical exponents. So there was a question last time about the non-renormalizability and vertices of higher order. We went through this when we were doing dimensional power counting, but I'm just going to review it quickly so that that question is addressed again, just making sure that every step of the way is pretty clear. All right, so what I'm going to do is review power counting and address that question. Remember that we discussed. Oh, it's been doing this. Oh no, it's working. We discussed a real scalar field in d space-time dimensions with the following action, right? Which is like minus half del mu phi squared minus half m squared phi squared, right? There's a mass term, there's lambda phi n term, right? I keep it phi n to just make a point. So what do Feynman diagrams look like? I don't know why this thing is not working. My pen is not working. It's okay. Oh, there we go. So there's a propagator, which is 1 over p squared minus m squared, and then here's a vertex, phi n vertex term. We said that if we have an arbitrary Feynman diagram, right? So an arbitrary Feynman diagram is a contribution to some endpoint, some amplitude, right? There will be a number of loops, L. There will be a number of propagators, a number of vertices, and they satisfy this relation, right? That's just geometry. Then because we have vertices where n legs meet, n times v is the number of vertices, is the number of external lines plus 2p. These were two identities that we had based on the geometry of the graph. Putting these together, we find that the superficial degree of divergence was dl minus 2p. D is space-time dimension. L is the number of loops, and this is the propagators. We rewrote that in this form, right? So this is the form we want to focus on. I don't know my pen salt is, the pen is being weird today. This is what we want to focus on. So space-time dimension is fixed, right? So we're not going to touch that. The number of legs, so if you are in higher than 2 dimensions, so 2 dimensions is a very special case. We said we have super normalizable theories, blah, blah, blah. In higher than 2 dimensions, this coefficient is negative, right? So as we go to higher vertices, the divergences are less severe, at least from the point of view of this term, the contribution of this term. But then there is this v term, the number of vertices, right? So higher point functions, as we go to higher orders in perturbation theory, they're going to have more and more vertices in them. If this term is positive, for every fixed value of n, there exists diagrams at some high order in perturbation theory that will blow up, right? So every diagram, every endpoint function outside coming in, for some value, some number of vertices in the diagram at some order in perturbation theory will blow up. That was a very definition of non-renormalizable theory. Non-renormalizable theory was something that every single amplitude, all amplitudes are divergent at large enough order in perturbation. So all of that will depend on the coefficient of this term, right? If it's positive, n times d minus 2 over 2 is minus d is larger than 0. This is precisely our definition of irrelevant operator, right? Because the dimension of phi n is n d minus 2 over 2. This you can recognize, right? It's about whether the term phi n is irrelevant. When phi n is irrelevant, then every amplitude at some order, large enough order in perturbation theory will blow up, and that's bad, right? So this was the connection. Does this address the question? Good. So clearly, if this term is negative, then you might be in a super lucky situation of super renormalizability, right? What was super renormalizability? Only Feynman diagram divergences, right? Renormalizability was only a finite number of amplitudes diverge. Good. Of course, when you have a normalizability, it's always lower point functions, right? That are divergent. Just because of well, I went through that. All right. So to repeat, you could do, yeah.
So like this necessarily implies that as you grow up, you need more counterparts.
If it's, you're asking if the theory includes in the action and non-normalizable term, an irrelevant term, right? If you want to, yeah, at every single amplitude is like divergent, right? Remember, how did we normalize the theory? We introduced a set of counter terms, finite number of counter terms, right? We calculated our correlation function, and like we showed that we use these number of variables to cancel divergences and lower loops. As we went to higher loops, we said, oh, we don't need to introduce new variables, right? We could repackage everything in terms of higher order. Remember that, as I said, as an effective field theory, there's absolutely no problem with renormalizing things at some order in perturbation theory. The thing is that we cannot push this perturbation to your arbitrary order.
So like if I have a diagram of some with some number of vertices, like if I know the local counting terms lower vertices, we have the thing that we can replace those local things with the higher vertices and make it so as a counter term to be higher.
Sorry, say it again. I did not understand.
So like if I know the counter terms for lower order diagrams.
Yeah.
And for the higher order diagrams.
So you introduce, first step of the Renormalized perturbation theory is that write down all the diagrams that are divergent, based on superficial counting. If that list is infinite, right?
I guess I was just wondering, like, using only a finite set of counter terms and just using them, I contain all those.
Sorry, there are two ways to talk about it. The question of whether an individual Feynman diagram blows up or not is not necessarily a physical question. The question of whether an amplitude blows up is a physical question, right? So renormalizability is this setup where the point of this counter term is to capture the divergences in the amplitudes. But of course, we go through them Feynman diagram by Feynman diagram, right? The physics is associated with amplitudes. The diagrams are just a calculational method. Now, there are these formal proofs that tell you that, oh, if you check such and such, if you listed all the diagrams in a certain order in perturbation theory, then higher orders are guaranteed. Because like as we go to higher order, the number of Feynman diagrams just grows insanely fast. So listing them is just out of the question. Good. All right. So to put all of this together, we said an elegant way, a quick way of seeing whether your theory is renormalizable, at least superficially or not, is to look at the couplings, the mass dimension of the couplings for every term in the Lagrangian. If every single term in the Lagrangian has positive mass dimensions, then they are all relevant terms. Then in the infrared, the theory is good. In the infrared, these terms grow, the UV is safe. You haven't included any relevant terms. We call them relevant terms are the things that grow in the UV or are larger in the UV, which mess up your Gaussian fixed point perturbation. Renormalizable theories are when you have only relevant or marginal deformations, right? Non-renormalizable theories, they have irrelevant. There are some irrelevant deformations. But once you have an irrelevant deformation, you're not even guaranteed that in the UV you're gonna have something local. An example, if you guys are curious, there's a TT bar deformation in 2 dimensions, where it's believed that the UV is a string theory. All right, any questions? So this was just a quick recap of the terms renormalizable and non-renormalizable, because we want these totally ingrained. Like we're just going to be using these terms all the time. Good. All right. So now with that said, let's just go back and review lecture 7. it's always helpful in discussing the grand picture of renormalization to have in mind the space of all couplings, right? This is the theory space. For example, if you're talking about a real scalar field, include all the terms that you could, right? All of them. It's an infinite dimensional space, right? And of course, we said that we studied this in this pointer. Okay, in larger than 4 space-time dimensions, we said that the only relevant operator is mass. So in this infinite dimensional space, under renormalization, this direction is unstable, right? Because under RG they just grow. Every other direction is stable. So just flow towards this like line, if you wish. In D equal 4, lambda phi 4 is marginally irrelevant. What does that mean? It means that naive dimension counting tells you that it's marginal. You do loop corrections and you find that it's irrelevant, which means that it grows, it decays in the infrared, right? It decays in the infrared, but very, very slowly, logarithmically slowly. Putting all of this together, it means that we concluded that interacting a real scalar field theory does not exist in 4 dimensions or above. Good? Yeah.
You mentioned that the lambda phi 4 basically logarithm grows or like decreases, which one?
Is marginally irrelevant. So what does that mean? It means that it decays in the IR, which means that the UV behavior is awful. That's what we mean when we say it doesn't exist, right? Or some people might say a real scalar field is trivial in 4 and higher dimension. That just means that all you have is massive free fields, right? It's a Gaussian theory. All right, good. So as you flow towards the IR, all you've got is massive free fields. When d is less than 4, we have new fixed points in the IR, right? We discussed this in epsilon expansion, d minus epsilon dimensions. And then we said, oh, if in d minus epsilon dimension, we're in this lucky situation where there is a new fixed point because there are 2 terms in the beta function. One of them is going up, the other one is going down. So they compete. There will be some lambda critical. This is this new point. I'm oversimplifying the theory space, but there will be a new. Oops. There will be a new fixed point. There will be a new fixed point, and if you are in the epsilon, small epsilon perturbation theory, then this is perturbative. So these beta functions that we calculate to 1 loop or 2 loop or whatever are under control. These equations are sensible. Of course, beta function non-perturbative will have zeros, but the perturbative calculation is not going to teach you about those zeros. Yeah.
Yeah, you made a comment here last lecture that in general there can be strongly coupled fixed points where the perturbation theory fits.
Absolutely.
Can you elaborate?
It just because it can be there. I mean, the no principle tells you that like it won't be there. Actually, we think, well, there are lots and lots of strongly coupled 2-dimensional CFTs, right? We know about, and there could be the endpoints of all sorts of RG flows. As a matter of fact, well, there are examples. There are, in lower dimensions, there are explicit examples of this. Usually, once things have become non-perturbative, you lose track of things. Unless there are some, there are, you know, like in more advanced quantum field theory, you learn about. So there are these based on, I don't know, maybe string theory or some other setups. We often have these conjectured flows between 2 fixed points. Nobody has ever constructed these RG flows, right? But there's a conjecture that if you take this operator, this CFT, deform it by some operator, this flows to another CFT. Like it's a conjecture. And the way people check this conjecture, they cannot prove it. They often check like symmetries, right? Symmetries should match. Anomalies are things that are some non-perturbative methods. So some non-perturbative data that has to remain nice under RG flow. So there are some clues you could gather from the very few non-perturbative techniques we have to test these conjectures. But proving these are just a little bit. So yeah. Good. Once we get to a non-perturbative RG, I might give some examples. All right, then we discussed the Callan-Simanzik equation. The Callan-Simanzik equation in one line is the equation that describes the running of correlation functions, right? And it has in it how correlation function responds to a change of scale. It has in it two key functions, beta function and gamma function. Beta function captures the renormalization of couplings, how the couplings of the theory depend on scale. And gamma function tells you about the renormalization of the fields, the wave functions of the field, the amplitude of the field, right? We will say a few more words about the gamma function today. All right, so there was a question regarding renormalized perturbation theory, and I'm just going to go through that Callan-Simanzik discussion a little bit slower. So recall how we did renormalized perturbation theory. We started with the I think I defined it the other way around, right? I think phi naught was z half r. Yeah, that's how I defined it, right? So this is the bare field, right? These are some renormalization, wave function normalization introduced by hand, and this is some renormalized field, right? Then we rewrote the bare action as the same action for renormalized field and renormalized couplings, and then a whole bunch of counterterms. But importantly, the counterterms are treated as interactions for the renormalized field. Okay? Then we looked at renormalization conditions. That is, if you stare at this action and treat these guys as interactions for the variables phi of r, you will end up calculating this diagram, for example, as a certain number of loops, so the 4-point function, at some energy scale, right? And you will have to, you're going to say this is equal to minus I lambda of r at that energy scale m squared, right? These are the Mandelson variables. This energy scale is the renormalization scale, right? Now, what this equation does is that you make a fixed choice of lambda of r, right? And a fixed choice of renormalization scale, it will fix these variables in terms of m such that this holds. So when you renormalize the theory at this level, doing renormalized perturbation theory, imposing the renormalization conditions, for fixed lambda of r, all the m dependence is in lambda of z, delta of z and delta of m. Delta of lambda, sorry. Right? It's the counter terms. All the m dependence is in the counter terms. Because we just want to solve this equation, right? Lambda of r doesn't have any m dependence at the moment.
Yeah, one quick clarification. The renormalized Lagrangian is independent of lambda, right? Oh, it should be.
It's independent of lambda. What do you mean? It's a function. It's the same Lagrangian we wrote. Every time we had lambda 0, we put lambda renormalized.
I see.
But lambda mean the cutoff, or?
Yeah, I was speaking of the.
Oh, you're talking about the here at this level, Lagrangian is just it's a rewriting of degrees of freedom. There's no cutoff in there, right? It's just it's the action functional. It's a rewriting of the action functional. Good. Is this part clear? This is actually already. Yeah. No, never mind. Already here is clear. The left-hand side has no m dependence. So if you were to calculate some m dependence, take some m derivative, it's all going to act on these characters. Right? This is something I pointed out. Keep this in mind. I'm going to take one extra step. Now, let's renormalize the theory at some scale m with some coupling lambda of r. So we fix lambda of r, we fix m. We're not going to touch them. Then we change the scale to bm, right? Using our normalization. And then we see that your coupling changes. Your lambda of r becomes lambda of r of b. Right? Good. So I can now talk about b del b. Or the way I was doing it before, I can just talk about m del m. This is the whole origin of it. So this way, I can think of lambda of r of m and renormalizing at scale m. This way of thinking about stuff tells you that your normalized coupling is a function of M, so is Z of M. Every time you find, so are normalization variables. Normal wave function normalization. Every time you find yourself confused about M and what is fixed, what's not, fix M, introduce a variable B. Right? That makes it cleans up the situation a little bit better. But this way of viewing stuff, the end result of the calculation is the connected correlator, for instance, for an endpoint function, for the renormalized fields with renormalized couplings that somehow you scale M. Of course, it will depend on scale. All right. Now, this is the equation I started with last time. The left-hand side is the endpoint function for bare fields, right? Calculated using bare couplings. There's no M dependence on this side at all. On the right-hand side, you have Z of M to the power of N over 2, the connected correlator of normalized fields for a lambda of R of M and N. Good? Because the right-hand side has no M dependence, MDDM, a total derivative with respect to M, should leave the right-hand side variant. Said differently, if you send M to M plus delta M, lambda of R to lambda of R plus del lambda of R, and phi R to 1 plus delta eta phi of R, remember that this the delta eta is capturing the dependence here, right? You should have a total variation that's 0. So D of Gn is dGn dm del M, dGn d lambda is equal to N p eta. Right? Because I've just put this on the other side. This last term is coming from putting this on the other side and linearize. All right. With this in mind, here is the beta function is M dl del lambda del M. This is the dependence of couplings on the scale, right? And here is the gamma function, which is the dependence of the field normalization on the scale. And the end result is your Callan-Simons equation. Is this clear now? I think last time I jumped in the middle, right? So when you read texts on renormalization, people could have like that, what is used, what is kept fixed, what's not kept fixed, what is running, what is not running. People use lambda, capital lambda. The cutoff sometimes is a thing that changes. Sometimes people like keep the cutoff fixed, they change M. Sometimes they have the M in this business that we're discussing, M and BM, renormalization and scale. If I was keeping that fixed, it roughly speaking plays the role of the cutoff, but right there are like, don't get confused. Every time you see someone formulates a renormalization group, just make sure you understand what is kept fixed and what's running, right? All right. And let me repeat again. If you are to find beta of lambda and gamma, as we did last time, using renormalized perturbation theory, the way you do it is just because all the M dependent, you renormalize your theory, all the M dependencies in the counter terms, you just go and take derivatives from the counter terms. I showed you, I flashed a bunch of equations last time. For generic dimensionless coupling lambda, and say scalar field, to the lowest order, the beta function in Gn is MDM of minus counter term for the lambda coupling plus half lambda sum over I to N del Zi. This N is the endpoint function, right? Because there are N fields in the endpoint functions. For each of them, you need the delta Z. If they're all the same, so they will be the same, right? But in principle, it could be phi 1 of x1, phi 2 of x2, right? You could have a bunch of fields that are different. And there are n of m, that's where it comes in. For example, in the case of QED, this equation, we quickly run through it, but it's just MDM, beta of E, right? The beta function for electric charge, because the coupling of QED is electric charge, right? The 3-point vertex. That's your lambda. Is MDM of minus E delta 1 plus E delta 2 plus E over 2 delta 3. If you recall, delta 1, delta 2, delta 3 were the three things that we introduced for the three divergent diagrams that we had in QED. What were they? Vacuum polarization, which was the 2 point of for propagator of photon. There was a self energy of the fermion, then there was a vertex. And then we said ward identities tell you that two of them are the same. Remember which two? All right, so we evaluated so these equations are not explicit, but we did evaluate delta 1, delta 2, delta 3 in one loop in perturbation theory. This semester and last semester, I don't recall. I think last time we did definitely. So you just plug the values in, you take derivatives, and you get the beta function for the QED. So does E grow in QED in the infrared or not? Well, you guys decide that. You will think about that. All right. Good. Any questions so far? So this is the summary of lecture 7. It was a long summary, but I wanted to do a longer one so that to make sure there are no gaps. So including masses, when I was writing the equations for beta function, right? I was often giving examples from massless free fields, right? So you might wonder why I was doing that. The origin of that, let me just say it in words first, and then we're going to discuss it. Remember that the perturbation, what we are doing in normalization group flow, what we're capturing is the response of the correlation function to scaling, to change of scale, right? So it would be a perturbation theory around scale invariant theory, which is massless. Even though we organize the Feynman diagrams in terms of massive free fields, Gaussians, from the point of view of the beta function, if you want to set up the perturbation theory, you will have to treat m squared as any other coupling that breaks scale invariance, and there will be beta functions associated with it, right? So you're going to treat m squared like any other couplings, and you're going to calculate it order by order. So its starting point is small. You have to deform it a little bit near the deformation, near the fixed point, right? Because if m squared is large away from the fixed point, it's just hard. It's just that perturbation theory is difficult. Because what's important is that we want to look at the response of the system to scaling. When m is large, the system is not transforming nicely under scaling. Good. So how do we include masses? We include masses like any other couplings, right? So here's my GN. This is the connected endpoint function of x1 to xm. Here's a coupling that depends on scale. M squared, I'm just going to list it as one of the couplings. Mass, right? Now, hopefully you won't confuse all the m's. I have the tendency of using, actually in QFT, we often use the same letter. Little m, large m, little lambda, large lambda, meaning very different things. Hopefully I'm not confusing you guys. Which means that you just like Calvin semantic is just trivial generalization of what we had before. You're going to end up with gamma m squared del m squared, right? And this gamma m is the response of minus m del m of ln of m squared. Good? All right. This is not to say that we cannot make progress for larger masses. It's just that it's harder.
You said that you have to start with some.
So you take the fixed point. Remember our conformal perturbation theory. You take the fixed point, which is massless, all couplings zero. You have to deform nearby. if you jump far away, going to first loop, second loop might not necessarily be capturing your beta function. Your beta function might not have a nice expansion. Right?
Like you need the definition because otherwise. You won't do the
Beta functions are there, but you need perturbation to calculate.
I know, like, for example, we got a 6-point vertex from a 4-point vertex, because we were kind of zoom in. So, is it possible to like get lower point vertices from 5-point vertices? Like reductions to lower point vertices from 5-point. Why we follow you?
Of course. Of course. Um. What you're asking is this, if you are gonna add to some CFD suffix some lambda phi n, is it possible to generate terms that are not sure? In general, the principle is that like once, so you see, this means that you look in this higher dimensional space, you moved a little bit off in some direction. Right? And as RG flow, there's no guarantee that unless there's some rule that some principle that tells you a term could not be generated. Will be generated.
Well, it's just diagrammatically.
Yeah, so I recommend just going through that integration of a thin momentum shell. All right. All right, so now a few things. Callan semantic is a statement that renormal correlation functions are invariant under the following change. Lambda of m going to lambda of m prime, m of m going to m of m prime, and m going to m prime, right? It's a function of lambda of m, capital M, and m of m. Now, why is this? What's the physics of this? The physics of this, sorry, is the statement that physical observables should be invariant under this transformation. If you recall in part 1 of the course, we said correlation functions are a set of observables of quantum field theory, but there are other observables we talked about. In particular, we talked about the S matrix. S matrix also must remain invariant under this transformation. So here's the transformation rule you can write down for the S matrix. The S matrix, like any other observable, cannot depend on the renormalization scale. Yeah.
This is my, I'm a bit confused. Is it things like the electron charge and observable, like the charge and electron, or is
At some energy scale. So you say the charge of the electron at this energy scale, you set up an experiment, you bring in two, so what is electron charge, right? It's a scattering, it's this diagram. Right? You have to scatter two legs, two electron, well, the electron comes and sends a photon. Now, what's the momentum of this guy? The strength of this coupling will depend on this momentum. So if you prepare your electrons at some energy scale, right, particular energy scale, then you read off an electron value, some electric charge value.
yeah, so by this definition won't be by this statement won't be right. You should consider a physical variable because physical observable because it's not invariant under changes of energy scales. I misunderstanding.
So yeah, okay. Maybe yeah, electron charge is a coupling. Couplings technically are not observables. They're deduced. Couplings are deduced from value of measuring correlation functions. So yeah, maybe this wording of it was a little bit strong. That all physical observables should be invariant under this.
So like would it be more accurate to say that like stuff like amplitudes and correlation functions are like the what do you call it the what we actually observe and electrons are what we derive from that.
Yeah, we deduce them. Yeah,
Okay, so it's not like
coupling.
at
Yeah,
the first level, those things are invariant and everything else everything you deduce from them might be scaled.
it is. It is. I think it's a correct statement to say that the observables are correlation functions and the S matrix. The value of the electric charge is a parameter we put in the Lagrangian as a machine to generate some predictable, like, well, it has to come up with predictions, and that value is deduced from the things that you read off, right? But in a sense, yeah, I think it's good. We also discussed the connection between correlation function and the S matrix. You guys remember that? Part of the course. LSC, yeah, exactly. Thank you. What was the connection? It was coming through the poles, right? Anyway. All right. So now next I want to talk about composite operators. This is something that is, I think it's a topic that's very dear to my heart. So far, we've been talking about in quantum field theory, we've been talking about the 2-point functions, 3-point functions, phi of x, phi of y, and things like that. But what happens if you try to define phi squared of x, right? Taking the limit of y going to x of phi x, phi y. You have already dealt with this. I just didn't bother you guys much with it, and I just pretended it's all cool. There's a term in the Lagrangian, the Hamiltonian, m squared phi squared. As a matter of fact, phi n of x, the Lagrangian, we're going to treat it as an operator. So how do we make sense of it? There are all sorts of divergences in this limit. What we did was we systematically removed these divergences from the Gaussian theory using what we call normal ordering, right? And then I used that thing and I said, oh, take this and run with it. In perturbation theory, we're going to be fine, right? So recall that normal ordering was an ad hoc, some sort of scheme to remove divergences in the Gaussian theory and define for you something we call phi squared, right? We could have defined something else, but that's what we picked. Now the question is, all right, so there is a way of defining composite operators. You could talk about phi of x. Phi of x is an operator at some scale. Sorry, phi naught of x is a bare field, right? We said that once we renormalize, the renormalized things, the renormalized fields become scale dependent, right? Now, if phi of r of x of m depends, how is it related to the bare fields? By this z of phi of m. If I take the phi squared, do I need a new renormalization variable, or is it just z of phi of m squared? It turns out that it's not z of phi of m squared. The fact that these two are not the same is something that's referred to as anomalous dimensions. So something that in the bare theory looks like you take an object and multiply it n times with each other. So this object originally, for example, scalar field, has scaling dimension in this in the massless free fields theory, had a scaling dimension d minus 2 over 2, right? So the scaling dimension of phi naught to a power of n was n times d minus 2 over 2, right? That seems sensible. Now, when you renormalize, is it true that the scaling dimensions are just like this? Are they going to add up? And the answer is no. And the fact that they are almost going to add up, but there will be corrections to it that we're going to call anomalous dimensions. Good? All right, so I'm just first going to present the grand picture, and then I'm going to give you an example with phi squared. As a matter of fact, in your theory, you're gonna have all sorts of crazy operators. There's always some sort of like a, I don't know, crazy operator you've defined in your theories, composite. And this guy will have its own renormalization. If we have multiple operators OP, and if there is no symmetry principle that forbids mixing them, OP of M will actually, you have to write it as a sum over P prime, Z of PP prime of M, O of P prime. So composite operators can mix. Oh, what happened? Okay. Composite operators can mix among each other under renormalization. I'm just trying to tell you some basic things. So if you're wondering why so far, every time where I was discussing RG, I was setting M equals 0 and talking about only about lambda phi 4. The reason is that once you introduce several of these operators, the flow will mix them. Right? So that's sort of why when I was in these spaces, the flows, I was not drawing them as a bunch of lines like this. I was drawing them like this. Right? The operators mix as you go along. So under RG, operators with same quantum numbers mix. Same quantum numbers means that there are no symmetry principles that forbids mixing. Now, again, similar to the Kalin-Simanzek, as we do for Kalin-Simanzek, you could define, you could write down M del M of Ln of Z of O of M, right? And that will give you something that depends on the couplings, the masses, and M, and that's called the anomalous dimension of operator O. So now let's go through an example to see why this is called anomalous dimension. Consider operator phi n. This is at point X and defined at scale M. This operator, by definition, is Z of phi n of M, phi n of X. Good. I'm gonna do a RG transformation. M goes to MB, X goes to X over B. Right? Under that transformation, this is just a number. It's untouched. Phi of n of X under this transformation transforms canonically with dimension that is in the UV, right? Because this is a UV beast. I should put zeros here. Yeah. So this guy is a UV field. It will transform like phi 0 of n, X over B, B to minus n, D classical. This is just a dimension counting from classical dimension counting because it's phi of n is n times D minus 2 over 2. Right? Now, using the same relation, I can write this down as phi of n of X over B MB at the cost of taking out a normalization factor like this, and I end up with this equation. Right? So if B is near 1, I'm just going to expand this, and I see that under the RG flow, phi of n of M and X, the renormalized composite operator, transformed in the way that's normal by some B to a power of the standard dimension suggested by the UV plus some gamma. That's the anomalous dimension. What is that gamma? That gamma, if you just expand this guy near B equal 1, you're going to obtain this term. So that's why we call this the anomalous dimension. It's about how composite operators scaling deviates from the standard thing. If you just added up the contribution, the scaling of individual constituents, right? So there's a contribution coming from there. And that has to do with the sort of like composite object is not just a bunch of non-interacting things. There are interactions, right? So, and that interaction means that this composite is just not the sum of their pieces, but there is a bit more. Now, of course, in perturbation theory, these guys are going to be small. These anomalous dimensions are going to be small in perturbation theory. But when we talk about a non-perturbative theory, if you recall, this composite operator can be such that the contribution of like its properties, whatever it is, for example, its dimension, right? Scaling dimension, could mostly come through the interactions and not it's not really a sum of its pieces. The interaction is so strong that it's a brand new emergent degree of freedom. That's what happens in RG flows when things get non-perturbative, and in infrared you end up with a bunch of degrees of freedom that are hard to relate the UV degrees of freedom. Because things pair up strongly. Good. So small anomalous dimensions is perturbation theory. Once they become large, it's wacky. Right? It's non-perturbative. This app has been doing weird things. I'm sorry. I did not pay to renew a subscription. I don't know why. That's why it's so buggy now. It worked for several years, fine. Sorry, let me just go out and come back. Maybe I shouldn't have touched it. Wow. Whoa. Yeah, this app has all sorts of bugs now. No. What did I do? Is there any way to close this? Hopefully it'll work now. Oops. Not gonna pay. Oh. All right. This is getting crazy. Sorry, guys. I don't know what to do now. Let's see. The previous lectures it shows, but not a. There we go. Okay, good. You just have to be stubborn, not pay the $14. All right, good. Okay, so what we said is that how an operator scales differently compared to its building blocks, right? Or to its naive power dimension counting is the UV fixed point, is the anomalous dimension. Good.
A bit off the topic question here. Can we think about this composite operators as reducible matrix elements? Since we see,
Is what, sorry?
can we think about this composite operators as some reducible tensors? So because
Reducible tensors.
yeah, tensor operators, like because here we see a mixing of the like operators with the same quantum numbers means the same thing happens for reducible tensor operators as well.
What is a reducible tensor operator?
Like if you perform a rotation operation or something on that, then for a specific rank, there's a mixing of the ranks of the tensor.
Like you can define essentially angular momentum.
Yeah, that's
for
what I'm
tensors.
saying. Exactly.
And if it has one angular momentum, then it's irreducible, but it can in general
Yes.
be like
in quantum mechanics.
be a bunch of.
Oh, are you talking about the, you're talking about EREPs of your, so.
Kind of.
Well, that's the starting point of any, yeah, okay, so, well, let's not worry about it, yeah. Remember that the starting point of quantum field theory the quantum field theory starts with representation theory of the symmetries we have, right? And if you start with just Poincare invariance, you write down the most general Poincare. You build your objects out of the representation theory of Poincare, which was mass and spin, right? If you have other symmetries, you will implement them, right? So, for example, CFTs, the starting point would be different. You would be looking at representation theory of the conformal group in D+1 dimension, which is SOD comma Q. So the conformal group in 1 + 1D is Anyway, all right. All right. Solutions of the Kalin-Simanzik equation. So far we just argued for Kalin-Simanzik. We have to, now I want to talk about the solutions of Kalin-Simanzik equation. How many of you guys know what the characteristic method for solving PDEs? You know it off the top of your head. I do not. So I'll walk you through it, right? It's a method to solve PDEs. And as you just saw, of course, the Kalin-Simanzik is a PDE, right? It's a function of m and a whole bunch of lambdas. So to simplify, you can think of it as just a function of m and one lambda, right? And yeah, so we're gonna discuss that. So Kalin-Simanzik, we're gonna study it for the case of massless lambda phi 4 real scalar field theory for the 2-point function. It doesn't get simpler than this. It's the cleanest form. All right, so we want to explicitly solve it. All right, based on the symmetries, you could easily argue, and we did argue, that the form of this is going to be I over p squared, right? P squared because it's massless, and some function of p squared over m squared. This m is now the renormalization scale. This is an ansatz, and this ansatz tells you that as you go deep in the UV, in the Gaussian fixed point, this G should become 1. All right, this ansatz has a consequence. If you take this G2 and act on it with this operator, it's going to give you 0. That's just a one-liner. You could check that explicitly. Now, what was the Kalin-Simanzik? Kalin-Simanzik was m del m plus beta lambda del lambda plus 2 gamma lambda of G2 is 0. This equation, this ansatz we took, allows us to, instead of evaluating m del m, replace it by derivatives of momentum. Good. So it's just rewriting my. At tree level, G2 is going to be minus I over p squared, which solves this, and beta lambda and gamma lambda are 0. Right? Good. All right. So we want to solve this equation. I traded m for p, or p over m. Right? So to make it even cleaner, I'm going to define a variable t, which is log p over m. This way, I have my G2 is a function of t and lambda. Good. And this is a PD that we'll have to satisfy. F lambda is just 1 minus gamma. I want to solve this PD. So the way we solve this PDE is using the method of characteristics, which was like Sidney Coleman has used this analogy that we're gonna reproduce here to teach you the method of characteristics using an example from biology. All right. So what's the analogy? Imagine you have a pipe. There's some fluid that's flowing through this pipe with some velocity v. Now, so it's water, some fluid is flowing, and there is a colony of bacteria that lives in this water, right? As the fluid moves around, the colony is just displaced, right? So, but if the density of bacteria at this point at time t equals 0 was x at this point, later on, the same colony is transported down. What we are after is the density of bacteria at some time t at point x along this pipe. So there are two things we're going to do. First, we're going to make the velocity position dependent, right, to make it a little bit non-trivial. Second, we're going to allow the bacteria to split. So as time goes by, they're going to also, the population is going to grow, right? So let's go slowly through this. of course, the first part is what I said, right? If the density of bacteria at point X at time T is D of X and T, at time 0, this is what the density was. If the velocity is independent of position. If velocity depends on X, D of X and T will satisfy this PD. Right? This is just like bacteria are being displaced. So far, they're not splitting. So let's forget about splitting for a second. This is just displacement. You can solve this differential equation to find where the colony that started at some initial point at here, well, at colony that started here at time t equals 0, where is that colony later on, right? By solving this differential equation. It moves to some x bar of t of x that satisfies this equation. All right, so this x bar of t of x is just telling you how the colony moves. What we want to solve is to allow for this minus or plus. I think it should be plus. No, minus. We want to allow for this rho of x function, which tells you about the growth rate of the colony. Right? And well, if you just want to know what happens to a colony at here, after some time t, this colony is displaced to some new position, and meanwhile they've been splitting. So there's an exponent growing that tells you about how like this colony is splitting. And now, if the rate of growth depends on the position, inside the exponent you have an integral. Right? So here it tells you where the initial colony is coming from. And here is telling you how it's splitting. Right? Good. There's another way of writing it, but this way is, I think I'm not going to use it all. So that's all you need to know, right? In this analogy.
I'm a bit confused. What is x bar over here?
X bar is about the location. So a colony started here at some x at point x at time 0, right? We're asking where is it gonna be at some later time?
Okay, so x bar is the position at some later time.
Yeah.
Fine.
So to make the analogy exact, you just swap the t variable for log of p over m. That's why I defined that variable t. X is the coupling lambda. V of x is the beta function of lambda. Rho of x is 2 gamma lambda minus 2, and d of x and t is the 2-point function. So you just plug this in. What you find is this. You find that the 2-point function as a function of t, which was log of p over lambda, right? As a function of energy scale, the momenta, external leg, right? Is g of where the coupling is at that energy scale. So the coupling, it will depend on the coupling, right? The coupling will evolve. And then meanwhile, you have to integrate by this, you have to multiply by this exponent, which is taking care of the growth of the renormalization of the operators. Right? The 2-point function, G2 is the 2-point function. Each of the operators is growing and the coupling is evolving. Right? So this is taking care of the growth of the renormalization. That's why it depends on gamma. Right? If you recall, this F is, where was F? F is 2, 1 minus gamma, right? So this is taking care of the renormalization, the growth of the coupling, and this is telling you that as you change the scale, the G2 that you calculate, you have to plug in the right couplings at that scale. What are the right couplings at that scale? It's a solution to this beta function equation. The same way that previously we solved x bar as the location of where the colony is, right? When it was not splitting. Here we're solving this differential equation to find what the lambda is going to be at different scales. Right? Assuming that you started with some initial conditions. This is in general the form of the structure of the solutions to Callan-Semantic. There's a part which is, so you want to calculate some correlation function at some energy scale and a bunch of couplings, right? You relate that to well, I'm trying to over explain now. I said what I said. All right, good.
In some studies started with G2 being I by P squared or something.
Yeah.
That's like true general. As a non-negative. Will always be.
Yeah, for yeah.
This is like always true.
Well, yeah, and yes, formally for 2-point function, formally. But massless, sorry, is formally true for massless real scalar field. Right? So what does it mean? It means that if I go and calculate in my theory, right, what beta function is to first order, right? I solve these equations, I plug them back in, I calculate gamma functions to some order, right? Call them gamma function actually, because gamma function is something else. Gamma is to some order, right? I plug them in and I solve this formula. If under the RG flow, your couplings are still order 1, you can trust this. Otherwise, this is way too formal. Right? You have to remain within the realm of perturbation. Because remember that you're flowing along this, right? You can only integrate flow around in the vicinity of the fixed point. Right? Away from it, you don't know how to find the derivatives. These derivatives are beta functions, right? Good. All right. So now we want to, I just want to mention critical exponents. So sometimes when you discuss, I've walked you through a million different ways of thinking about it, keeping various mass scales in the problem. I personally, my favorite way of viewing RG is a setup where you take your couplings, remove the dimensionality out of them, and talk about dimensionless couplings. That's, in my opinion, one of the simplest ways of presenting it, right? Remember that, like, every time we're dealing with couplings, dimensions, because we're dealing with things of this type, it didn't matter, right? So B del B and M del M, we're just like interchangeably using it. But that's why it's okay. But like conceptually, I find it easier to work with dimensionless couplings. So I just want to walk you guys through that. And along the way, we're going to make a comment regarding what the anomalous dimension is and what's the meaning of critical exponents. I don't know how much I'm going to get into depth given the time. Start with a fixed point of the RG. That means the scale invariant theory, conformal invariant if it's relativistic. Deform it by a bunch of operators OIs. These are the couplings. This is the term we've included. Right? Here I didn't tell you what OI is. It could be a composite operator. It won't matter for the purpose of the conversation. Now, if OI has dimension delta I can write it in a dimensionless form in this way, where I've explicitly taken out the dimensionality of M and written it in terms of dimensionless couplings rho of I. This is Peskin's notation, and hopefully in the future I will not use T of I, but usually I use T of I. All right, so if I don't do this, my Callan-Semantic already looks like this, right? So this is my GN is a function of M and just all CIs, these are dimension full, right? So I'm gonna write it, I want to take M del M. There will be this is just the explicit dependence on M. This is N gamma that's coming from the fact that there's wave function normalization, right? Of these guys. And then sorry, It should be systematic. Yeah. Good. So each gamma I is for one of these guys, plus sum over I, m del m of del ci del ci. It's just a full derivative, right? And m del m of del I del ci is gamma I ci, right? That's what we do every time we define these guys. Hopefully it's clear why I put a ci here, because this guy was dimension full. So I want to take del I of log of it with respect to del, sorry, I want to take del of log of it with respect to del of m, so that I read off the exponent. When you have y of x and you take del of y as a function, del of y, del log of x, you're reading off the exponential dependence of y and x, right? You're reading that y equal x to the power of alpha, you're reading that alpha. That's the exponent. Right? These are all about the critical exponents or scaling dimensions. All right. Now, change of variables. We already introduced this variable t log of p over m. So ddt of ln of rho I, the dimensionless couplings, is going to be gamma I minus d plus delta of I. This is a one-liner. Think about why, because we're running out of time. Plugging this back for the connected correlator written as a function of dimensionless couplings, you find the following Callan-Semantic equation. This is just like, sorry, I still have to add some I gamma I. This is just like the good old, yeah, this is just a replacement we've done. These are the beta functions. Is that good? As we said, if you want to solve this equation, what you have to solve is that you have to solve the flow of the dimensionless couplings, the beta functions. You have to solve the beta functions for dimensionless couplings, and this is the equation you're trying to solve. All right, you solve that, you find that rho I bar, the bar is in the same notation as we call them bacteria, is rho I m over p d minus delta of I minus gamma of I. This gamma of I is the anomalous dimension. Now, in perturbation theory, we said this gamma of I is small, so it could be neglected near a fixed point, but in principle, it's not. Good? This is just a few lines of algebra. So let's make it a little bit less abstract by going through an example. Consider the operator phi squared, right? What is the coupling associated with this operator? M squared, it's just mass term. At the Gaussian fixed point, this rho of M is the dimensionless coupling associated to the phi squared, right? Is rho of M times M squared over P squared. This dependence comes from this power because D minus delta of I is D minus 2, right? Each phi is D minus 2 over 2, phi squared is D over D minus 2, and D minus, parentheses, D minus 2 is just 2, so it's M squared over P squared. This means that mass grows in the IR, right? As P goes towards 0, mass, the coefficient, the dimensionless mass grows, right? That's why it's a relevant operator, always, independent of the dimension. Because this power came off as 2, independent of D. D is canceled. Now, if for some reason you have a non-trivial fixed point at some lambda star, then there will be these anomalous dimensions associated at that value of lambda, and your equation will be modified this way. A new fixed point means that another conformal field here, right? Is this clear? So in the remaining couple of minutes, I'm just going to interpret this term and this new fixed point. All right, so remember the solution to a 2-point function Kalan-Semantic equation. So the formula looked like this. This was the part that was the running of the coupling, G2 at the new value of the coupling, and this had to do with the renormalization of the wave function. We wrote this for G of P, right? G2 of P, momentum space. T, remember, is log of P over M, right? In Fourier space, we Fourier transform and write it in real space. So this would the 2-point function real space. I wrote Y so that we could do the Fourier transform itself. But the 2-point function real space, G2 of X, is G2 of the coupling, will depend on the coupling at that. Now X represents your scale in a sense. And then this is a renormalization value. You end up with an integral from 1 over M to X, d of log of X bar, lambda of this. I won't bother you with that, but I just want to say that if you add a fixed point, this guy is going to come out as independent of X. So it's just lambda of X, lambda star. This integral you could do explicitly. You end up with this expression, which could be simplified as 1 over X to the power of d minus 2 plus 2 gamma lambda star. So what did we find? We found that the 2-point function and this new fixed point, as you separate the operators, falls off not as with a critical exponent. It shows a critical exponent, it shows critical behavior. You guys know what critical behavior means? Maybe. I'll try to comment on that this time. But the anomalous dimension is telling you about how the 2-point function decay, the power, the critical exponent has changed. Right? It's a brand new CFT, so there are new scaling operators. But what we found was that one of the old scaling operators became a brand new scaling operator with a new eigenvalue for the dilatation operator. So you could think of this as a deformation of the theory, where the spectrum of the spectrum of dilatation operator goes from some values to some other values. All right. Any questions? Let me do a 3-minute summary of what we discussed. Yeah.
This one was like clarify what you said at the end. So we started from one CFT, they were deforming, and accordingly, it reached lambda star, that it reached another CFT.
Yes.
Okay.
Right, that's a new fixed point. I assume there's a new fixed point. Like for example, in the case of in the epsilon expansion, you can find one.
Okay.
All right, so what did we discuss today? A lot of stuff. As usual, I forget the beginning. So we addressed the question of this why higher orders of phi over phi n or higher powers of field phi or derivatives, including in the Lagrangian, as what we said, this irrelevant operator. It's not kosher. It gives you non-renormalizable theories, but you wanted to see it from the point of view of power counting. We reviewed that. Okay, Kalan-Semantic, all of that we had discussed before. I tried to make a point about so last week I jumped in with this equation. So I tried to elaborate a little bit more about the dependence on M. Where is the dependence on M and how we get Kalan-Semantic equation. I said that to include mass inside Kalan-Semantic equation, you have to treat it like any other coupling, because Kalan-Semantic is capturing the response of the correlation functions of the theory. The beta function, or it's a response to scaling, right? Change of scale, right? And the fixed points are scaling invariant theories that are massless. So from the point of view of scaling, mass is just another coupling. We said that S matrix also satisfies an equation, a similar equation, because it has to be independent under these transformations, right? Renormalization transformations. We talked about composite operators, how normal ordering was a way to define composite operators in Gaussian theory. And we said in general, in prediction theory, composite operators, as you do renormalization group, need not have their canonical dimensions. They might end up with anomalous dimensions, and that just means that the wave function normalization of a composite operator is not the wave function not a multiplication of the wave function normalization of its constituent pieces. It has extra stuff in it, right? And we said that when you're doing normalization, all operators that are allowed to mix will mix in general. So if there's no reason for that forbids this, they will mix. We explicitly showed that when you do a tiny Euclidean momentum interval integration, which is small b, you end up with anomalous dimension, which is basically log of m del m of this ln of the composite operator, right? It's just an anomalous dimension. We talked about formally solving the Callan-Siemens equation. The answer came out as you integrate the beta function equations for the coupling. You find the new coupling at the scale of interest. You plug that in G2. You have to multiply it by the part that's taking care of the renormalization of the wave functions, and that just involves exponent of an integral over gammas, right? Is that good? That's was a formal structure of it, that we ran this analogy of Coleman with bacteria. And the rest is, I think, a bunch of examples about scaling dimensions and critical exponents. Any questions? Yeah.
There are two questions. First is that we argued that the beta function, philosophically, it was related with how couplings depend on scales, and your gamma function was related to the amplitude of fields, right?
Yes.
Now, when I was treating mass as a coupling, I saw that my gamma function got changed instead of the beta.
Your gamma function got?
My gamma function changed, right? When I was treating mass as a coupling in the Callan-Siemens equation.
So the gammas are functions of the, for each field you have a gamma, right? So there's a gamma that you have to include for each field. And so there is that part, but then for every coupling, you end up with a beta. So M is treated as a coupling. Of course, the running of the dependence of gamma on M and beta on M are related, because you have to solve the Callan-Siemens equation. Callan-Siemens explicitly tells you what is the thing what kind of cancellation should happen. But from that point of view, M is like any other lambda. So if you took lambda phi4 massless theory, the change of dependence of Z or gammas on M will be related to lambda on M. Right? So same thing will work for mass.
All right. And the second question is this: what can you think of about the significance of these anomalous dimensions?
Significance of anomalous dimensions. Well, anomalous dimensions. Correlation length is the significance. When you have a 2-point function, as you separate them, let's say your system has a whole bunch of scales, energy scales, right? Each energy scale will give you a length scale. This correlation function will be a function of the distance of this translation variant. When you make distance much larger than the all inverse mass scales in the problem, right? At that regime, there are no masses that we can write. So if I have a 2-point function, right? So I have a phi of r, O of r, O of 0. How is this gonna behave? What can I write? I can write, sorry, let me write over here. I can write 1 over r to some power. That's one behavior I can put. I'm gonna put 2 delta. Or I can put e to minus r over some c. I can sum over a whole bunch of these guys with a bunch of coefficients, right? So let's forget about the sum. Let's just say there's this behavior and then there's this behavior. This behavior requires a dimension, it requires a length scale. So in the regime where R is much larger than all the length scales in the problem, these guys, even if they exist, they're just gonna go away. So you're gonna be, the only thing you can write down is 1/R to the power of some power. And this power is the scaling power of this. It's the energy, like the mass dimension of this operator O. When this is anomalous, means that the mass dimension of your operator has changed. Right? So this is the thing, this is the part that we're talking about. Correlation length is over here, right?
It looks very similar to what we do in mean field theory or in Ising models, right?
Well, this is statistical field theory, exactly. So statistical field theory is in the regime, you start with some stat system, you're going the limit either because of tuning near a continuous phase transition, you go to the limit where your correlation length goes to infinity. So, yeah. Sorry, I said something wrong. I said something wrong. If you go. Yeah, okay, never mind. I'll try to include some discussion of statistical field theory in the next lecture. Any other questions?
Mass always goes with to, how do we end up with this?